For 2 decades, the American Meteor Society has been watching the sky, logging every fireball, cataloguing every report, building the largest civilian database of atmospheric impacts on Earth. And in all that time, across all that data, they have never published anything quite like what appeared on March 25, 2026, a confirmation that the fireball anomaly is real, and they cannot explain it. A 7-ton asteroid over Ohio, a meteorite through a roof in Houston, sonic booms across multiple states, and green fireballs lighting the sky from California to Washington. And then, 3 days after the dataset closed, a new fireball screamed over Washington state at 39,000 miles per hour, as if the sky had not quite finished making its point. The American Meteor Society looked at all of it, ran it against 20 years of records, and confirmed what some had quietly suspected. Something had changed, but they do not know what. They do not know why. They do not know when it will stop. Tonight we are going to walk through exactly what they found, why every explanation they tested fell apart, and what is rumoured to come next. Stay with me. This one is worth it. If this has you hooked, subscribe to the Skylab and tell me what you think below. After the asteroids, the sonic booms, the meteorite through someone's roof, is the solar system trying to get our attention, or is something out there simply breaking apart? Either way, we're about to find out. Let's get into it. Part 1. The line that changes everything. On March 25, 2026, a scientific paper landed quietly. No press conference, no fanfare, no dramatic announcement. Just a published analysis from the American Meteor Society, sitting in a database waiting for someone to read it carefully enough to understand what it was actually saying. So let me read it carefully for you. The American Meteor Society operates the largest civilian fireball database on the planet. Not the largest in one country, not the largest in one hemisphere. The largest on Earth, full stop. They have been collecting continuous data since 2005, and their platform has been running in a stable, methodologically consistent form since roughly 2016 to 2018. That matters, because when a database this size, this old and this stable tells you something has changed, you listen. And what they are telling you is this. The anomaly is statistically real, it is physically significant, and it is unexplained. 3 conclusions, clean, measured, from the most credible civilian source for this kind of data that exists anywhere in the world. Not a fringe researcher, not an online forum, not someone connecting dots on a whiteboard at 2 in the morning. The American Meteor Society went to their own data, ran their own analysis, and came back with findings that surprised even them. Now, before this paper came out, here is where the conversation was living. People were noticing patterns, forums were lighting up, videos were getting made, yes, including on channels like this one, pointing at the number of fireballs being reported in early 2026 and asking whether something unusual was happening. And the standard response from official channels was predictable. More people have phones, more people are outside, more cameras. Reporting is up, therefore events appear up. Nothing to see here. Move along, that explanation is now under serious strain. Because here is what changed with this publication. This is no longer a conversation about pattern recognition and speculation. This is a conversation about database-level statistical confirmation. There is a difference between noticing something feels off and proving, with 2 decades of comparison data, that the pattern is real. The AMS just did the second thing, but here is where it gets genuinely interesting, and stay with me on this because the framing matters enormously. The question is not simply, are there more fireballs? That question on its own is almost too easy to deflect. Of course reports go up, everything goes up. More cameras, more people, more internet connectivity, more platforms to submit reports to. That argument has legs, and the AMS knows it has legs, which is why they did not stop at counting events. The question they asked, the question that makes this paper different is this. Why are the larger objects increasing disproportionately? That is a different question. That is a harder question. That is a question that the more cameras explanation does not comfortably survive. Think about it this way. If you increase the number of observers in a system, you increase your detection of everything proportionally. Small events go up, medium events go up, large events go up. The ratio between them stays roughly constant. You have added sensitivity uniformly across the board. What you do not expect, what you cannot explain by adding cameras, is a scenario where the small events increase modestly and the large events increase dramatically. That would mean you have not just added observers, you have added objects, specifically large objects. That is what the data shows. The AMS calls this a distribution shift. The size distribution of incoming material appears to have changed, not the total number of objects at the small end of the scale, but the proportion of material arriving at the high energy end. The curve has moved. Something has pushed it. And when I tell you the AMS paper itself is cautious, data-driven and explicitly uncertain, I want you to understand what that means in scientific terms. These are not people prone to alarm. These are people who spend their careers filtering noise from signal, who understand reporting bias intimately because they live with it every day, and who have just published findings that they openly admit they cannot fully explain. The language in this paper is not sensational. It is the opposite of sensational. It is the careful, hedged, measured language of researchers who found something they did not expect and are being honest about the fact that they do not yet know what it means. That honesty, in a strange way, is the most alarming thing about it, because the numbers look normal until you zoom in. And when you zoom in, everything changes. Part 2. The detail everyone missed. Here is a number that will initially underwhelm you. 2,046. That is the total number of fireball events recorded by the AMS in the first quarter of 2026. 2,046 events, and yes, that is the highest quarterly total ever recorded. But, and this is the critical but, it is only marginally above past years, not dramatically, not wildly, just slightly. If you looked only at that headline number, you would probably shrug and move on. That is exactly what almost everyone did. But the researchers did not stop at the headline number. They did something more precise, more revealing, and ultimately far more disturbing. They applied witness count thresholds to the data. Instead of just counting events, they started asking a different question. How many events generated a significant number of independent witness reports? And here is why that methodology matters. Witness count is a proxy for something real. It is a proxy for object size and brightness. A small, faint fireball burning up high in the atmosphere might generate 2 or 3 reports from people who happen to be outside looking at the right patch of sky. A large, luminous, low-altitude fireball that produces a sonic boom and lights up a region like a second sunrise is going to generate reports from hundreds of people who are not even looking at the sky. They just suddenly found themselves unable to ignore it. The number of witnesses does not just scale with how many people are watching, it scales with how impossible the event is to miss. So what the AMS did was sort their data by this threshold. Events with 25 or more reports, events with 50 or more reports, events with 100 or more reports. And at each level they compared 2026 to the historical average. At the 25 report threshold, the increase is about 42% above historical average. Noticeable, significant. But you could still, at a stretch, attribute some of that to increased platform awareness, more people knowing to submit reports, social media driving traffic to the AMS website after a sighting. At the 50 report threshold, it doubled. 38 events versus a historical average of 18, not 42% higher. Double. That is harder to explain with reporting enthusiasm. At the 100 report threshold, the events so large, so bright, so physically impossible to miss that they generate triple-digit witness counts from across entire regions, also doubled. 14 events versus a historical average of 7. Notice the pattern. The signal does not weaken as you raise the threshold, it strengthens. The anomaly exists only at the high energy end of the spectrum, and this is the line that collapses the reporting bias argument, because here is the fundamental problem with that explanation. If the anomaly were driven by increased reporting, more people submitting, more awareness of the platform, more social media amplification, it would affect all thresholds proportionally. Everyone getting more diligent about reporting would mean more reports for small events, more reports for medium events, more reports for large events, roughly equally. The ratio between them would hold. What does not happen in a reporting increase scenario is the anomaly growing stronger as events get larger. That pattern specifically suggests that the large events themselves are increasing, not just the number of people telling you about them. Now let's talk about March specifically, because March is where this data stops being a statistical curiosity and starts becoming something that demands a physical explanation. In March of 2026, 5 fireball events generated more than 200 witness reports each. 5 events in a single month, above 200 reports. To put that in context, that is more than all previous Marches in the entire AMS database combined. Not more than last March, more than every March on record, added together. The average witness count per major event in March 2026 ran at approximately 142. The previous historical high for a single March was approximately 49. That is not a small deviation. That is not noise in the data. That is a near tripling of the intensity signal in a single month. If these numbers reflect real physical objects entering the atmosphere at higher energies, there should be evidence beyond the numbers themselves. Measurable, physical, independent evidence. Something you can hear, something you can hold in your hand. As it turns out, there is. Part 3. The month that broke the model. Let me walk you through what March of 2026 actually looked like. Not as statistics, but as events. Because when you put them in sequence, the picture that emerges is not the picture of a normal month. On March 8th, a fireball detonated over Europe with 3,229 witness reports, a number so far above the historical average that it reads almost like a data entry error. It was not. Ground teams recovered meteorite fragments classified as diogenite, a rare type of space rock that we will come back to, because it matters more than it initially appears. 9 days later, on March 17th, a 7-ton asteroid entered the atmosphere over Ohio. 7 tons. The energy release was estimated at the equivalent of 250 tons of TNT. That is not a rock. That is an event. People in multiple states reported shaking ground, rattling windows, and a sound they initially mistook for an explosion or a gas line failure. 4 days after that, on March 21st, a meteorite penetrated the roof of a building in Houston, Texas. Went through the roof, into a room. That is the kind of event that people tend to remember. March 23rd brought dual fireball reports from California. 2 separate events, same general region close in time. March 24th added further events across the Midwest and Southeast. Step back and look at that timeline. March 8th, March 17th, March 21st, March 23rd, March 24th. Multiple high-energy events clustering within a span of 16 days. And here is the detail that matters for understanding what this clustering actually means. None of these events are associated with known meteor showers. This is not the Perseids. This is not the Leonids. This is not a predictable annual stream with a known radiant point that Earth passes through on a calendar schedule. Meteor showers have a source. They have a direction. Every meteor in a shower traces back to the same point in the sky because they are all pieces of the same cometary debris trail that Earth intersects at the same point in its orbit every year. These March events, they come from different directions, different radiants, no common source that has been identified. What do you call a cluster of high-energy impacts with no common origin, no known stream association, no seasonal explanation, arriving within days of each other across 2 continents? The AMS does not have a clean answer for that. The best framing available is something I keep coming back to as I read through the data: patterned chaos. Events that cluster in time without clustering in space or direction. Events that feel organized but lack the organizing principle that would make them explainable. The geography of these events makes the clustering even stranger. Europe on March 8th, Ohio on March 17th, Houston on March 21st, California on March 23rd, Midwest and Southeast on March 24th. North America and Europe both hit within the same 16-day window, by objects from different directions. Repeated sonic boom reports accompanied multiple events. And the meteorite recoveries were not just rocks, they were diogenites and eucrits, members of the HED meteorite group, types of space rock that make up only about 3 to 4% of all meteorite falls. More on that in a moment, because the rarity of those rock types is a clue pointing somewhere specific. But here is the thing you need to know right now. Even as significant as this sequence is, the dataset that captured it was already closing. The AMS analysis covered data through March 24th, and the sky was not done. Part 4. The update that shouldn't exist. The AMS dataset for this analysis closed on March 24th. The paper was published on March 25th, and then, on March 28th, Zhongtan State got hit. The fireball arrived at approximately 39,000 miles per hour. It was tracked along a path from roughly the Wilkson area toward Carr Inlet. 100 witnesses reported the event. NASA's Space Alert System detected it independently, and with 100 or more reports, this single event would, under the AMS methodology, qualify as a major high-energy fireball. That makes it event number 11 above the 100 report threshold in March alone. Except it is not in the March dataset because the dataset was already closed. Think about what that means for a moment. The AMS published a paper confirming a fireball anomaly in March of 2026. That paper documented 10 events above the 100 witness threshold, and then, 3 days after the dataset closed and 4 days before the paper published, an 11th event happened. An event that by every metric the paper uses to define significance would belong in that analysis and is not in it. This is not a criticism of the AMS. You have to close a dataset somewhere. You cannot keep adding data indefinitely and still publish. But it does mean something important. The phenomenon that the paper confirmed is not a closed historical artifact. It is not something that happened in March and is now safely in the past tense. It is ongoing. The anomaly was still producing major events even as the researchers were finishing their analysis of it. And this raises a genuinely uncomfortable question about the timeline we're working with. The March 28th Washington event was confirmed by NASA's Independent Detection System. This was not an ambiguous sighting, not a bolide that only showed up in one camera network and might have been a satellite re-entry or a weather artifact. This was a real, fast-moving, high-energy object entering the atmosphere over the Pacific Northwest, confirmed by 2 independent systems, 3 days after the AMS confirmed that March 2026 was already the most anomalous month in their database. What does it mean when the paper documenting a fireball anomaly is outdated before the ink is dry? It means the phenomenon is evolving faster than the analysis. It means whatever we think we know about what happened in March, the true picture may already be larger. The AMS confirmed something that was, at the moment of confirmation, already understating itself. If you're keeping a mental count of how many independent lines of evidence are pointing at the same conclusion, that the high-energy end of the fireball distribution is behaving in a way that has never been recorded before, that count just went to one more. But witness counts and timelines are one kind of evidence. If the objects are genuinely larger, the physics of atmospheric entry will show it in ways that numbers alone cannot. And that physical evidence exists. It is loud, it is measurable, and it cannot be faked. Part 5. Sonic booms, the unfakeable signal. There is a sound that a large meteor makes when it enters the atmosphere fast enough and dense enough to survive deep into the air column. It is not the crackle of a distant firework or the low rumble of thunder several miles away. It is a pressure wave, a physical disturbance in the air itself generated by an object moving at hypersonic velocity through a medium it was never meant to survive. Windows shake, car alarms trigger, people call emergency services. You cannot report bias your way into a sonic boom. Out of the 38 large fireball events documented in the AMS analysis for this period, 30 produced sonic booms, 30 out of 38, that is 79%. Now, you might look at percentages from previous years and find similar ratios. Some years have shown high sonic boom rates among their large events. But here is the crucial distinction, and it is the kind of distinction that separates a meaningful anomaly from a statistical coincidence. The anomaly in 2026 is not just a high percentage, it is a high percentage combined with a dramatically elevated absolute count. Let me make that concrete. If you had 5 large fireball events in a typical year, and 4 of them produce sonic booms, your rate is 80%. Fine. But if you have 38 large events and 30 of them produce sonic booms, your rate is still 79%, but now you have 30 sonic boom events instead of 4. That is not a ratio anomaly. That is a volume anomaly, and it is confirmed by physics. A sonic boom from an incoming space rock tells you several things simultaneously. It tells you the object was moving fast, which is essentially guaranteed for anything entering from space, so that is not the interesting part. More importantly, it tells you the object was large enough and dense enough to penetrate deep into the lower atmosphere before it fragmented or slowed significantly. Small meteors burn up high and fast, dissipating their energy in the upper atmosphere where the air is thin, generating light and heat, but rarely generating pressure waves that reach the ground. Objects that produce sonic booms have made it down into the thick part of the air column, which means they started big. Translate that frequency into something human-scaled. 30 major sonic boom events in approximately 90 days. That works out to roughly one significant sonic event every 3 days. One major object, large enough and dense enough to shake windows and rattle rooftops, arriving approximately every 72 hours. Now remember the central question here, the one the AMS paper is actually asking. Has the size distribution of incoming material changed? The sonic boom data is not ambiguous. It is not subject to reporting bias. You cannot manufacture a pressure wave by submitting a report to a website. You cannot accidentally hear a sonic boom because someone else posted about a fireball on social media. These are physical events, recorded by physical instruments felt by physical bodies, and they are telling the same story as the witness count statistics. Something is arriving at higher energies than before, and the sonic booms are the atmosphere's own way of confirming it. But there is a second physical signal, completely independent of witness counts and sonic boom records, that tells the same story in a different language, and almost nobody is talking about it. Part 6. The duration spike nobody's talking about. The AMS database recorded 1,693 long-duration sightings in this period. Long duration, in the context of fireball observation, means 4 seconds or longer. A 4-second fireball is not the streak of light that catches your eye for a fraction of a second and is gone before you can register it. It is a sustained, moving, luminous event, visible long enough that you have time to react, point, call someone over, start your phone camera. The previous record for long-duration sightings in a comparable period was 651. That record was set in 2021. 1,693 versus 651. The current figure is not just above the record, it is more than 2.5 times the record. Now, why does duration matter? Why is this an independent physical signal rather than just another way of counting the same phenomenon? Because fireball duration is controlled by physics, not by observers. When a piece of rock or metal enters the atmosphere, the length of time it remains luminous depends on 2 primary factors: how large it is and the angle at which it enters. A larger object carries more mass and therefore more thermal energy to burn through before it either fragments completely or slows below the incandescence threshold. A shallower entry angle means the object spends more time travelling through the atmosphere's visible layers before it exits the other side or disintegrates. In either case, duration is a function of the physical properties of the object itself, not of how many people are watching it. You cannot get a 4-second fireball by having more observers. The object either lasts 4 seconds or it does not. What you can get by having more observers is a higher detection rate for 4-second fireballs that would have otherwise gone unrecorded. But here is the problem with that explanation in this context. The duration data is climbing at a rate far beyond what increased observer density can plausibly explain. 2.5 times the previous record is not the expected output of a gradually expanding reporting network. This is the second independent line of physical evidence pointing at the same conclusion. Independent from witness counts, independent from sonic boom frequency, derived from a completely different observational metric and yet converging on the same signal. Larger objects, more energy. Higher mass material entering the atmosphere and taking longer to burn. There is also an observational consequence of duration that connects directly back to why witness counts are so elevated. Objects that burn for 4, 5, 6 seconds are visible across dramatically larger geographic footprints. A 1-second fireball might be seen from a radius of 100 miles under good conditions. A 6-second fireball, travelling at 20 miles per second, has moved 60 miles across the sky during its visible phase, potentially illuminating a swath of territory spanning multiple states. Of course, it generates more reports. It is physically covering more ground. The high witness counts and the high duration figures are not 2 separate anomalies, they are 2 manifestations of the same underlying phenomenon. These objects are not just brighter, they are lasting longer, and some of them are not burning up at all, some of them are making it through. Part 7. Meteorites on the ground. 3 recoveries stand out from this period, and they stand out for reasons that go well beyond the basic fact of meteorites landing near populated areas. The Ohio Fall, connected to the March 17th event, was classified as a eucrate. The Germany recovery from the March 8th bolide was classified as a diogenite. A chondrite fell through a roof in Houston. 3 meteorites recovered from 3 separate events within a period of less than 2 weeks. And if you are the kind of person who finds that mildly interesting, stay with me, because by the end of this section, you're going to find it considerably more than mildly interesting. Let's start with the chondrite, because it is the one we can dispatch relatively quickly. A rock came through someone's roof in Houston. That is dramatic. That is the kind of thing that makes national news and generates a very awkward conversation with your insurance company. But in terms of what a chondrite tells us about where this material is coming from, the answer is not much that is new. Chondrites are the most common kind of meteorite by a significant margin. They make up the overwhelming majority of all recorded falls. They are, in the meteorite world, the equivalent of finding a common pebble on a beach, still a rock from space, still worth examining, still objectively remarkable when it lands in your living room, but not a signal that points toward anything unusual about the source population. The Houston chondrite earns its place in this story through sheer audacity of delivery. Scientifically, it is not the rock that should be keeping researchers up at night. The eucrite and the diogenite are an entirely different matter. To understand why, you need a brief introduction to a family of meteorite types that most people have never heard of and which are, quietly, some of the most scientifically significant rocks that ever reach the ground. Eucrites and diogenites are both members of a group called HED meteorites. The name comes from the 3 types in the family: howardite, eucrite, and diogenite. And what makes this family remarkable is not just their chemistry, though the chemistry is fascinating. What makes them remarkable is their origin. HED meteorites are believed to come from a single parent body, not a generic rocky asteroid, not a fragment of some anonymous chunk of solar system debris, but a specific identifiable named object. The leading candidate, supported by decades of spectroscopic analysis comparing the meteorites to remote telescope observations, is 4 Vesta, one of the largest objects in the entire asteroid belt. An object approximately 525 kilometers in diameter, ancient enough to predate the formation of the planets as we know them, and geologically complex in a way that most asteroids simply are not. Here is what makes Vesta unusual among asteroids. Most asteroids are essentially undifferentiated, meaning they formed as relatively uniform mixtures of rock and metal without ever getting hot enough internally to separate into distinct layers. Vesta is different. Vesta got hot enough, early enough in solar system history, that it underwent a process called differentiation. Its interior melted and separated by density, with heavier metals sinking toward the center and lighter silicate rocks floating toward the surface. It developed a core, a mantle, and a crust. It became, in miniature, something resembling a planet, and then it froze in place, geologically speaking, while the actual planets continued evolving around it. What this means for the meteorites is that eucrites and diogenites are not just pieces of rock. They are pieces of a specific geological layer of a specific body. Eucrites come from the crust. Diogenites come from the mantle, or lower crust. They are chemically and mineralogically distinct from each other in ways that reflect their different depths of origin within the same parent body. Finding one of these meteorites is finding a piece of ancient planetary geology, a fragment of a world that started becoming a planet and then stopped. HED meteorites make up approximately 3 to 4% of all meteorite falls. In the context of a year where hundreds of meteorites might theoretically be recovered globally, a single HED fall is notable enough to generate scientific interest. Recovering 2 HED falls within 9 days of each other is statistically remarkable. The probability of that happening by chance, given the base rate of HED falls in the overall meteorite population, is low enough that researchers pay attention when it occurs. But the detail that elevates this from statistically remarkable to scientifically fascinating is the directionality problem. The calculated entry directions for the Ohio eucrite and the Germany diogenite are separated by approximately 98 degrees, nearly a right angle in the sky. These 2 rocks, both chemically fingerprinted to the same parent body, arrived at Earth from almost opposite directions. And this is where the story gets genuinely strange. If both of these rocks came from Vesta, or from the Vesta family of smaller asteroids that were knocked off the parent body by ancient impacts, they should broadly share similar orbital characteristics. Material ejected from the same source body tends to cluster in orbital space, at least initially. The Vesta family is a well-characterized group of asteroids whose orbits reflect their common origin. They are not spread randomly across the solar system. They occupy a recognizable region of orbital parameter space. So why are these two rocks coming in from directions nearly 90 degrees apart? Why are they not arriving from broadly the same region of the sky as you would expect from two fragments of the same parent population? There are a couple of ways to approach this apparent contradiction, and neither one is entirely comfortable. The first resolution is time. Asteroid family members do not stay neatly clustered forever. The same gravitational forces that shape planetary orbits, the subtle tugs of Jupiter, of Mars, of the Sun's own oblateness, gradually spread family members into increasingly divergent paths over millions and billions of years. A fragmentation event that happened early in solar system history could, by now, have dispersed its products across a wide enough range of orbital inclinations and orientations that two fragments arrive at Earth from completely different directions while still carrying the same chemical signature. This is known to happen. It is not a speculative mechanism. It is an observed feature of how asteroid families evolve. The second resolution is more recent and more interesting. If the fragmentation event that produced these specific fragments happened not billions of years ago, but in the geologically recent past, perhaps thousands to hundreds of thousands of years ago, the debris would not yet have fully dispersed. But a more recent disruption could still produce divergent trajectories if the initial fragmentation was energetic enough, if the parent object was already moving in a complex orbit, or if secondary gravitational interactions with other bodies altered the paths of individual fragments shortly after the event. The test that could distinguish between these scenarios is a technique called cosmic ray exposure age analysis. When a rock is part of a larger body, it is shielded from the high-energy cosmic radiation that constantly streams through interplanetary space. The moment it breaks free as an independent fragment, that shielding is gone, and cosmic rays begin altering specific isotope ratios within the rock in ways that accumulate measurably over time. By analysing those isotope ratios, researchers can calculate approximately how long a fragment has been travelling through space as an independent object, its exposure age, measured in millions of years, thousands of years, or anywhere in between. If the Ohio Eucrit and the Germany Diogenite have similar cosmic ray exposure ages, if both rocks spent roughly the same amount of time as independent fragments before arriving at Earth, that would be powerful evidence for a common originating event. It would mean they were liberated from their parent body at approximately the same time, sent onto independent trajectories by the same disruption, and arrived here within 9 days of each other after travelling those trajectories for however long the exposure ages indicate. That analysis is almost certainly underway right now. The Ohio meteorite is in the hands of researchers. The Germany Diogenite has been recovered and is being studied. The laboratories that do this kind of isotopic work move carefully and publish when they are confident, which means the answer may exist already in some form, sitting in a spreadsheet, being checked and rechecked before anyone commits it to a paper. And if the exposure ages match, if the data confirms that both rocks were set loose at the same time, from the same event, on trajectories that only diverged over the course of their independent journeys through space, then something broke. Relatively recently, somewhere in the Vesta family. A body that had survived billions of years of solar system violence was disrupted, and the pieces are arriving here now, chemically announcing themselves to anyone paying close enough attention to recognise them for what they are. The sky sent us 2 calling cards from the same address. We are still waiting to find out when they were mailed. Part 8. The Distribution Shift. Let me take a step back from individual events and individual numbers and try to describe what the AMS paper is actually saying at its most fundamental level, because the central finding here is not about any single spectacular fireball, not about the asteroid over Ohio, or the rock through the Houston roof, or the green streaks lighting up the California sky. Those events are vivid and memorable, and they make for compelling footage. But they are symptoms. The AMS paper is about the underlying condition. And to understand that condition, you need to understand a concept that sounds technical but is actually, once you see it, almost intuitive. It is called a distribution shift. And it changes everything about how we interpret what happened in early 2026. Start with a mental picture. Imagine placing every meteoroid that enters Earth's atmosphere on a scale, from the smallest to the largest, and then counting how many objects fall at each size. If you plotted that count as a graph, you would get a curve that is heavily weighted toward the small end. Tiny particles, the ones that burn up as brief flickers of light on a clear night, the shooting stars you make wishes on, vastly outnumber everything else. They are essentially uncountable. They arrive constantly, day and night, in numbers that would surprise most people if they knew. As you move along the scale toward larger and larger objects, the numbers drop off. Medium-sized objects are less common than small ones. Large objects are less common than medium ones, and the truly enormous impactors, the civilization-scale events, are so rare that their average recurrence interval is measured in millions of years. This is not a bell curve in the technical statistical sense. The actual distribution of meteoroid sizes follows what mathematicians call a power law, where each step up in size brings a roughly proportional step down in frequency. But for the purposes of understanding what the AMS found, the conceptual picture of a curve weighted toward the small end and tapering toward the large end is exactly right. That is the normal state of affairs. That is what the baseline looks like. That is what 20 years of AMS data established as the expected pattern. A distribution shift means that curve has moved, not across its entire length, not uniformly from small to large, selectively, specifically at the high energy end. The small events in early 2026 increased modestly, in a way that is broadly consistent with expanded reporting, more cameras, more platform awareness, more people knowing where to submit a sighting. That part of the curve behaved the way you would expect it to behave if you simply added more observers to the system. Nothing alarming there. But the medium events did not behave that way. The medium events increased at a rate that would previously have been associated with large events. And the large events, the ones generating 50, 100, 200 witness reports, increased at a rate that would previously have been associated with extraordinary once-in-a-decade occurrences. The whole upper portion of the distribution slid to the right on the scale, toward higher energies, higher masses, deeper atmospheric penetration. The curve did not grow taller uniformly. It grew taller specifically where you least want it to grow. This is the finding. This is what the AMS confirmed. And once you understand it, the threshold analysis that we walked through earlier takes on a new clarity. Remember the pattern. At 25 reports per event, the increase above historical average was about 42%. At 50 reports per event, it doubled. At 100 reports per event, it doubled again. The signal grew stronger as the threshold rose. That is not what a reporting increase looks like. A reporting increase would produce roughly proportional gains at every threshold. What the AMS observed is disproportionate gains at higher thresholds, which is precisely and exactly what a distribution shift would produce. The mathematics of the threshold pattern is not just consistent with the distribution shift. It is a signature of one. It is the fingerprint of a curve that has moved at its high energy end. And now, here is where the picture becomes something more than a statistical argument. Because the beautiful and somewhat unsettling thing about this conclusion is that it does not rest on statistics alone. The physical evidence we have already examined maps onto it with a precision that is hard to dismiss. Consider the sonic boom data. 30 out of 38 large events producing sonic booms, a rate of 79% combined with a dramatically elevated absolute count. Sonic booms require objects to penetrate deep into the lower atmosphere before they dissipate their energy. Small objects do not do this. They burn up high, where the air is thin, converting their kinetic energy into light and heat without ever generating pressure waves that reach the ground. Objects that produce sonic booms are large enough and dense enough to survive the upper atmosphere and make it into the thick, resistive lower air column before they slow significantly. The elevated sonic boom frequency is exactly what a distribution shift toward larger objects would predict. If the curve moved toward higher energies, more objects would be large enough to reach sonic boom depths. The data confirms this prediction. Consider the duration spike. 1,693 long-duration sightings, defined as 4 seconds or longer, against a previous record of 651. Duration is controlled by object size and entry angle. Larger objects carry more mass and therefore more thermal energy to burn through before they either fragment completely or decelerate below the luminosity threshold. A population shift toward larger objects would produce exactly the kind of duration spike the AMS recorded. A 2.5 times increase over the previous record is not a subtle nudge in the expected direction. It is a dramatic confirmation of the same underlying signal expressed through a completely independent measurement. Consider the meteorite recoveries. 3 falls in under 2 weeks, including 2 HED meteorites from the rare Vesta family, representing rock types that together account for only 3 to 4% of all falls. Meteorites reach the ground because their parent objects were large enough and dense enough to survive atmospheric entry. A distribution shift toward larger, denser incoming material would increase the probability of ground-level recoveries. It would also, and this is the more subtle point, increase the probability of recovering rare meteorite types simply because rare types are present in the overall population at their natural frequency. And more large objects reaching the ground means more of everything reaching the ground, including the 3 to 4% that carry the HED fingerprint. Now step back and look at all of this together. Witness count statistics collected by a public reporting platform. Sonic boom data derived from independent witness descriptions and infrasound sensor records. Long-duration sighting counts measured by timing reports from observers across multiple continents. Meteorite recoveries confirmed by physical laboratory analysis of recovered samples. These are not 4 versions of the same measurement, they are 4 genuinely independent measurements, collected by different methods, analysed by different researchers, subject to different sources of error and bias. The probability that all 4 would simultaneously and independently point toward the same conclusion, a distribution shift toward larger incoming objects, if no such shift had actually occurred, is vanishingly small. This is what scientists mean when they talk about convergent evidence, not one strong signal, multiple independent signals that all arrive at the same place. Each one alone might be explainable by coincidence or artifact. Together, they constitute something much harder to dismiss. The size distribution of incoming material shifted in early 2026. The statistics confirmed it. The atmospheric physics confirmed it. The recovered chemistry confirmed it. 3 independent lines of evidence from 3 different domains of measurement, all reading from the same underlying reality. What the AMS confirmed, in the careful and hedged language of researchers who understand the weight of what they are publishing, is that something about the population of material arriving at Earth changed. The curve moved. The high-energy end got heavier. What they did not confirm, what no one has yet confirmed, is the answer to the question that naturally and immediately follows. If the distribution shifted, something shifted it. If the curve moved, something moved it. If larger material is arriving in greater numbers, that material came from somewhere, was set in motion by something, and is following a trajectory that began at a specific point in space and time. The AMS confirmed the what, the why, and the where, and the when it started. Those questions are still open, and following them to their edges leads somewhere that is, depending on your disposition, either fascinating or deeply uncomfortable, probably both. Part 9. The Anthelian Surge. Every night, as Earth rotates and the sky turns overhead, there is a region of space called the Anthelian source. It sits roughly opposite the Sun in the sky, the direction Earth is coming from as it moves along its orbital path. Think of it as the cosmic equivalent of looking out the back window of a moving car. You're seeing the direction you just came from, and in that direction, material tends to drift into your path simply because you are moving toward it. Under ordinary circumstances, this region produces a steady, predictable trickle of meteors. Not a shower, not a burst, just a background hum of material drifting into Earth's path from the general direction of the solar system's ecliptic plane. Astronomers have been watching it long enough that they know its rhythms the way a sailor knows the tides. Reliable, consistent, boring even, in the best possible way. In the first quarter of 2026, it doubled. Let that land for a moment before we move on. Not increased slightly. Not ticked upward in a way that required statistical nuance to detect. Doubled. Anthelian activity in this period reached densities of approximately 9.6 events per 1,000 square degrees. That number may not mean much on its own, so here is the translation. It represents roughly twice the activity levels recorded in previous measurements of this source across comparable time periods. A source that has been studied, catalogued, and characterized as one of the most stable background features of the meteoroid environment has suddenly started producing twice as much material as anyone has previously recorded it producing. To appreciate why this is significant, You need to understand what the Anthelian source actually represents in physical terms, because it is not just a convenient point in the sky that astronomers use as a reference. It is a window into a specific orbital population. Objects that reach Earth from the Anthelian direction are not random visitors passing through the neighbourhood on their way somewhere else. They are residents. Material travelling in low inclination, roughly circular orbits that keep it confined to the inner solar system on a long-term basis. These are not comets falling in from the outer system on dramatic hyperbolic trajectories, swinging past the Sun once every few centuries. These are objects that have been circulating in the inner solar system for a long time, their orbits gradually shaped and refined by the gravitational influence of the planets until those orbits intersect Earth's path. This distinction matters enormously for what the doubling implies. If the Anthelian surge were being driven by an influx of new cometary material from the outer system, you might expect to see it reflected in other directional populations as well, and you might expect the objects to have the high-velocity, low-density characteristics of cometary fragments. What you are seeing instead is an increase in a source that specifically reflects the inner solar system's resident population. Whatever is driving this surge has its roots close to home, orbitally speaking. When a stable, well-characterized source like this doubles its output, there are two broad categories of explanation worth considering. The first is structural. Earth's orbit is not a perfect circle through a perfectly uniform distribution of material. It is a path through a solar system that has clumps, concentrations and gaps, regions where material has accumulated over time due to gravitational resonances, past collision events, or simply the gradual herding effect of planetary gravity. It is entirely possible that Earth, in its eternal annual journey around the Sun, has moved into a section of its orbital track that happens to be denser than usual in the Anthelian direction, a natural clump, a patch of higher than average material density that Earth is currently sweeping through and will eventually sweep out of. The second explanation is more recent in its mechanism and in some ways more consequential. Something may have injected new material into this region of orbital space recently enough that it has not yet dispersed. A disruption event, a collision between two inner solar system objects, a fragmentation of a larger body whose pieces settled into the low inclination orbits that feed the Anthelian source, could produce exactly the kind of sustained elevation we are observing. The material would not arrive all at once. It would filter in gradually as the debris dispersed along its new orbital paths and began intersecting Earth's trajectory at the Anthelian point. The result would look, from the ground, like a background source that had simply decided to become twice as active. The phrase I keep returning to when I think about the second scenario is something feeding the background. That is not language from the AMS paper. It is my characterization of what the data implies. But the logic is straightforward. Background sources do not spontaneously increase their output. They are fed by something, either Earth moving through a denser region or a new source adding material to an existing population. In the absence of a known dense clump in this section of Earth's orbit, which would presumably have been detected and documented during previous passes, the feeding hypothesis carries some weight. Now, here is something worth sitting with for a moment as we think about what the Anthelian surge means in the context of everything else we've been discussing. The distribution shift we documented earlier, the finding that the high-energy end of the fireball-sized spectrum has increased disproportionately, is consistent with the debris injection scenario. Fresh material from a recent disruption event would not be the finely ground dust of ancient, well-processed asteroid families. It would include larger fragments, pieces that have not yet been ground down by millions of years of collisions with other debris. Larger fragments arrive with more energy. They produce brighter fireballs, longer durations, sonic booms, and occasionally meteorites. A recent debris injection feeding the Anthelian source would produce exactly the kind of size distribution shift the AMS confirmed. These two findings, the Anthelian surge and the distribution shift, are not being presented to you as independent coincidences that happen to be occurring at the same time. They are potentially two observable consequences of the same underlying event, seen from different analytical angles. One tells you that a familiar source is suddenly more active. The other tells you that the material arriving is skewed toward larger sizes. Both point toward the same general hypothesis. Something added fresh, relatively large material to the inner solar system's resident debris population in the Anthelian orbital region. What that something was remains unconfirmed. The AMS paper does not name a specific event or object. They describe the pattern and note that it is consistent with Earth intersecting an uncharacterized debris population, a scientifically careful way of saying that the material is real, its effects are measurable, and its origin has not yet been pinned down. But the Anthelian surge is not the only directional signal in the data. There is a second population of incoming objects behaving anomalously in early 2026, and it tells a different and, in some ways, even stranger story than the Anthelian source does. Because the Anthelian source represents the residents of the inner solar system, the low inclination, roughly circular orbit population that has been circling close to the Sun for a long time. That is one kind of incoming material, and its doubling is already significant. But the second anomalous population in this dataset is not from low inclinations. It is not from the familiar ecliptic plane where most of the solar system's material resides. It is coming from somewhere else entirely, from directions that imply orbital histories that are dynamically distinct from anything the Anthelian source could produce. And when you put the two anomalies side by side, an inner solar system source doubling and a high inclination population also doubling simultaneously, the combined picture stops looking like a coincidence and starts looking like a system under stress from multiple directions at once. The Anthelian source is half the picture, and the half we have not yet examined is the one that is harder to explain, harder to account for with familiar mechanisms, and harder to dismiss as anything other than a genuine signal from a part of the sky that should not be sending one. Part 10. The High Inclination Problem. 11 events in the first quarter of 2026 had radiance above plus 70 degrees declination. 11 events originating from very high angles relative to Earth's orbital plane. The previous maximum for a comparable period was 5. Take a moment with that comparison before we go further. 5 was the previous record, 11 is the new number. That is not a marginal increase. That is not the kind of fluctuation that gets absorbed into the normal year-to-year variation that researchers expect and account for. That is more than double the previous high in a single quarter from a directional population that has never before behaved this way in the recorded dataset. And when you understand what high inclination arrivals actually represent physically, the number stops being a curiosity and starts being a puzzle with some genuinely uncomfortable implications. So let me give you the orbital mechanics orientation I promised, and I will keep it as gentle as possible, because the geometry here is actually not that complicated once you have a mental picture to work with. Imagine the solar system as an enormous flat disk. Not perfectly flat, not perfectly uniform, but broadly planar in a way that reflects its origin. 4.5 billion years ago, the solar system began as a vast rotating cloud of gas and dust. As that cloud collapsed under gravity, it began spinning faster, the same physical principle that makes a figure skater accelerate when they pull their arms toward their body. And as it spun faster, it flattened. The material that would eventually become the planets, the asteroids, the comets, and the debris fields we are discussing tonight did not settle into a random three-dimensional scatter. It settled into a disk, a broad, roughly planar structure with the Sun at the centre and everything else orbiting within it. Earth orbits in that disk. Mars orbits in that disk. Jupiter, whose gravitational influence shapes so much of what happens in the inner solar system, orbits in that disk, and the overwhelming majority of the debris that populates the inner solar system, the asteroid families, the cometary trails, the background meteoroid population, orbits in that disk as well, their paths tilted only modestly relative to what astronomers call the ecliptic plane, the reference plane defined by Earth's own orbit around the Sun. This is why the Anthelian source behaves the way it does. The material it samples is disk material. Low inclination, roughly circular orbits, residents of the inner solar system who have been circling within the plane for a long time. When you look toward the Anthelian point, you are sampling the population of objects that share Earth's broad orbital neighbourhood in the most literal geometric sense. They travel in the same plane. They approach from directions close to the ecliptic. They are, in the most fundamental way, part of the same flattened disk that produced Earth itself. Objects arriving from declinations above plus 70 degrees are something else entirely. To reach Earth from that high above the ecliptic plane, an object must be travelling on an orbit that cuts steeply across the disk rather than within it. Picture a coin lying flat on a table. That is the ecliptic plane. Now picture a second coin standing nearly upright, its edge intersecting the flat coin at a steep angle. The orbit of a high-inclination object looks like that second coin. It does not circulate within the plane of the solar system. It crosses through it, diving steeply below the ecliptic on one side of its orbit and rising steeply above it on the other, intersecting the plane only briefly during each pass. Getting into an orbit like that is not easy. It does not happen through ordinary solar system dynamics operating on timescales we would consider recent. There are essentially three pathways that can produce a high-inclination orbit, and none of them are unremarkable. The first is ancient history. During the early solar system, when the giant planets were still migrating into their current positions, gravitational interactions between those planets and the smaller bodies surrounding them were chaotic and violent. Jupiter in particular scattered enormous quantities of material onto highly elliptical and highly inclined orbits. Some of that material ended up in the outer solar system, in the scattered disk and the Oort cloud. Some of it found its way onto long-period cometary orbits that carry it back toward the inner system every few thousand or million years. When these ancient travellers arrive, they carry the orbital signatures of that early chaos: steep inclinations, high velocities, trajectories that cut across the ecliptic at dramatic angles. These are the solar system's oldest wanderers, and their high inclinations are a record of the violence of the system's formation. The second pathway is slower and more gradual. An object that begins in a modest orbit can have its inclination gradually increased over millions of years through repeated gravitational interactions with a massive body. Jupiter is again the primary agent here. Its gravitational reach extends across the asteroid belt and influences the orbital evolution of countless smaller objects over geological timescales. Through a process called secular resonance, where the gravitational interaction is not a single dramatic encounter, but a sustained, rhythmic tugging that accumulates over many orbits, Jupiter can pump up the inclination of an asteroid's orbit until it no longer resembles the low inclination path it started on. This is a slow process. It operates on timescales of millions to tens of millions of years. But it is a known, documented mechanism that has produced genuinely high inclination objects from originally unremarkable starting orbits. The third pathway is the one most directly relevant to what we're observing in early 2026, and it is the most dynamically violent of the three. A sufficiently energetic collision between two objects in the asteroid belt does not just break both objects apart. It imparts a range of velocities and directions to the resulting fragments, and depending on the geometry of the impact, some of those fragments can be launched onto dramatically inclined orbits. The collision itself provides the energy needed to kick material out of the ecliptic plane. The resulting fragments do not need millions of years of Jovian perturbation to acquire their inclination. They get it immediately, in the moment of impact, from the kinetic energy of the collision itself. A recent high-energy collision in the asteroid belt could therefore inject a population of fragments onto high-inclination orbits on a timescale of years to decades rather than millions of years. Those fragments would begin crossing Earth's orbit relatively quickly, and they would arrive from directions well above the ecliptic plane, from declinations above plus 70 degrees for instance, because their inclined orbits carry them high above the disk before sweeping back down to intersect Earth's path. The previous record of 5 events from this high-inclination population tells us that such objects exist in the near-Earth environment and occasionally reach us. 5 events in the previous record means this is not a completely exotic phenomenon. Earth sweeps up high-inclination material from time to time. The background rate is low but measurable, and researchers who have been studying the AMS data for years were aware of this population without considering it anomalous. 11 events changes that assessment. 11 events against a previous maximum of 5 in the same quarter that saw the Anthelion source double, the large fireball threshold statistics double, the long-duration sighting record shattered, and 2 rare HED meteorites fall on separate continents within 9 days of each other. 11 high-inclination events in that context is not a background fluctuation. It is a signal. And it is a signal that does something critically important to the shape of the explanation space. It makes simple explanations structurally impossible. Here is why. If the entire fireball anomaly of early 2026 were driven by a single source, one debris stream, one disrupted parent body, one concentrated patch of material that Earth happened to intersect, the directional data would cluster. The radiance of the anomalous events would point back toward a common origin, the way every meteor in the Perseid shower points back to the same radiant point in the constellation Perseus. Single-source events have directional signatures. That is one of the primary ways meteor astronomers identify and characterize streams in the first place. The 2026 data does not cluster, it spreads. The Anthelian surge is coming from low-inclination, inner solar system resident orbits, close to the ecliptic plane. The high-inclination population surge is coming from orbits that cross the ecliptic at steep angles, from directions nearly perpendicular to where the Anthelian events originate. These two populations are not just different in their numbers, they are different in their fundamental orbital character. They represent material with different formation histories, different dynamical pathways, different regions of origin within the solar system, and they are both elevated simultaneously, in the same quarter, in the same data set, confirmed by the same analysis. Two independent orbital populations, dynamically distinct from each other, both more than doubling their activity in the same 3-month window. The probability of that happening by coincidence, of two unrelated populations independently surging at the same time for separate reasons, is low enough that the coincidence explanation deserves considerable skepticism. What it suggests instead is something with a broader reach, not a single debris trail that Earth crossed, not one recently disrupted asteroid sending fragments along a narrow orbital corridor, something that affected the inner solar system's debris environment across multiple orbital regimes simultaneously, something whose influence was wide enough to elevate both the disk population and the high-inclination population at the same time. The sky is not behaving uniformly. The elevated activity is distributed across orbital populations that have no obvious reason to be correlated. And that distributed, multi-directional character is itself the most important clue in the entire dataset, because it tells you what kind of explanation you need. You need an explanation with a wide reach, one that operates across orbital populations rather than within a single stream, one that could plausibly affect both the low-inclination residents of the inner solar system and the high-inclination crossers that cut through the ecliptic plane from above. What that explanation looks like and whether the data is sufficient to identify it is exactly where the investigation leads next. And the answer, when you follow the directional evidence to its logical conclusion, is not the kind that resolves cleanly into reassurance. Part 11. The explanations that failed. The AMS did not simply publish their findings and leave the question of causation open. They tested the obvious explanations against the dataset, systematically, carefully, and one by one, those explanations failed. This is worth dwelling on before we get into the specifics of each failed explanation, because the process of elimination is itself a form of evidence. When a scientific institution with 2 decades of comparison data and a methodology refined over years of operation goes looking for the most charitable alternative interpretation of an anomaly in their own database and cannot find one that survives contact with the numbers, that is meaningful. Researchers are not, as a general rule, eager to publish findings they cannot explain. Unexplained anomalies attract attention, generate questions the institution may not be equipped to answer publicly, and invite the kind of scrutiny that makes careful scientists uncomfortable. The AMS had every professional incentive to find a mundane explanation, and publish that instead. They looked, they tested, they could not find one. So let us walk through the elimination process the way they did, because understanding why each explanation fails is as important as understanding what the anomaly actually shows. Increased reporting was the first and most obvious candidate, and it deserves the most thorough treatment because it is the explanation that sounds most plausible to a general audience, and the one that gets invoked most reflexively whenever fireball numbers go up. The logic seems reasonable on its surface. More people have smartphones. More people know about fireball reporting platforms like the AMS website. Social media amplifies sighting events, directing witnesses to submit reports who would otherwise have simply watched the sky and gone back inside. The AMS platform itself has grown its user base substantially over the years. Of course, more reports are coming in. Of course, the numbers look elevated. It is just cameras and connectivity, not rocks. The problem is arithmetic. If increased reporting were the primary driver of elevated fireball numbers, it would affect all fireball sizes proportionally. Think about what a reporting increase actually means in practice. More people submitting reports means more people who saw any given event are now telling you about it. The small events they previously ignored now get logged. The medium events they previously forgot about now get submitted. The large events they previously reported anyway now get reported by even more people. The entire distribution shifts upward roughly uniformly because the increase in reporting propensity applies to observers of all event sizes equally. What the AMS data shows is not a uniform upward shift. It shows a flat baseline at the small end of the distribution and a dramatic increase at the high energy end. The events generating 25 or more witness reports increased by about 42%. The events generating 50 or more reports roughly doubled. The events generating 100 or more reports also roughly doubled. The signal grows stronger as the threshold rises. That is the opposite of what a reporting increase produces. A reporting increase would show its strongest effect at the low end, where previously unreported small events are now being captured for the first time, and its weakest effect at the high end, where large, unmissable events were already being reported by many witnesses before the platform expanded. The threshold pattern in the 2026 data is arithmetically inconsistent with reporting bias as a primary driver. Not slightly inconsistent, structurally inconsistent. The math does not work. New meteor showers were the next candidate, and this one fails on different grounds entirely. The shower hypothesis requires a new source, a comet that recently disrupted and laid down a fresh debris trail that Earth is intersecting for the first time, or a previously uncharacterized stream that has somehow escaped detection until now. Both scenarios are theoretically possible. Comets do disrupt. New streams are occasionally identified, but a meteor shower, by definition, has a radiant. All the meteors in a shower trace back to the same point in the sky because they all originate from the same debris trail, which Earth intersects at the same geometry year after year. The shower's radiant is its signature, the directional fingerprint that identifies it as a coherent population rather than a random scatter. The events that constitute the 2026 fireball anomaly do not share a radiant. They arrive from multiple directions simultaneously. The Anthelian source surge brings material from low inclination, inner solar system resident orbits close to the ecliptic plane. The high inclination population surge brings material from orbits that cut across the ecliptic at steep angles, from directions nearly perpendicular to the Anthelian events. A single new meteor shower cannot simultaneously produce elevated activity from two orbital populations that are dynamically unrelated to each other. You cannot draw one line through points that are scattered in multiple directions and call it a stream. The geometry simply does not permit it. Seasonal effects presented a slightly more nuanced challenge, because there is a real and documented phenomenon that the AMS had to account for carefully. Researchers in meteor science have long noted a tendency for fireball activity to be modestly elevated in late winter and early spring, a pattern sometimes called the February effect. The mechanism involves Earth's orbital position and the geometry of the interplanetary debris environment at that point in the annual cycle. Earth's velocity vector, the direction it is travelling through space, shifts in a way that slightly increases its cross-section for sweeping up material from certain orbital populations during this period. The effect is real. It is not imaginary. And the AMS knows about it intimately because their database spans enough years to have characterized it thoroughly. The problem is scale. The February effect in the AMS historical data produces modest elevations, a few percent here. Some years a bit more, some years barely detectable. It is a background seasonal variation that researchers note and factor into their comparisons when looking at year-over-year trends. What the 2026 data shows is not a few percent, it is doublings. The February effect, operating at its maximum documented strength, would not move the large event threshold statistics from their historical averages to twice their historical averages. It would not produce 5 events above 200 witness reports in a single March when the previous record for all Marches combined was lower. Seasonal variation is a real signal. It is not the signal. The anomaly exceeds it by a margin that makes seasonal effects a footnote rather than an explanation. Time of day and geographic bias were the final conventional explanations on the list, and these required the most methodologically careful treatment. Fireball reporting has known temporal and geographic patterns. Evening hours generate more reports than daylight hours, because people are more likely to be outside and looking at the sky after dark, and because fireballs are more visible against a dark background. Certain geographic regions generate more reports than others because population density determines how many potential witnesses are present for any given event. The eastern United States, Western Europe, and parts of East Asia are consistently overrepresented in global fireball databases relative to their actual share of Earth's surface, simply because more people live there and more of those people have access to reporting platforms. The AMS factored these biases into their analysis. They applied the corrections that their methodology has been refined to apply. The temporal distribution of the anomalous events does not cluster in evening hours in a way that would suggest observational bias. The geographic distribution of the anomalous events does not concentrate in high population regions in a way that would suggest reporting density effects. The events are distributed across times and locations in a pattern that the bias corrections do not dissolve. After adjustment, the anomaly persists. Every conventional explanation tested, everyone found insufficient. The reporting bias argument fails on arithmetic. The new shower hypothesis fails on directionality. The seasonal effect fails on scale. The temporal and geographic biases fail to survive methodological correction. The AMS language documenting these failures is measured and technical, as you would expect from a scientific institution publishing in a peer-reviewed context. But read carefully. The measured language describes something significant: a thorough, systematic search for the comfortable answer, conducted by the people best positioned to find it if it existed, coming up empty. We know what the anomaly is not. It is not cameras. It is not new showers. It is not the season. It is not when people are watching or where they happen to live. What remains, after every alternative has been tested and set aside, is a real physical change in the incoming material itself. A change in what is actually entering the atmosphere, not in how we are detecting it. And that conclusion, uncomfortable as it is for an institution that would clearly prefer a tidier answer, is what the AMS published on March 25, 2026. But there is one more thread. One remaining possible contributor that the AMS considered carefully, could not dismiss, and ultimately could not fully quantify. It sits at the edge of the analysis, neither confirmed nor eliminated, and it is in some ways the most interesting loose end in the entire investigation, not because it explains the anomaly, but because of what happens when you examine how far it can and cannot reach. The explanation is plausible enough to take seriously, and it fails in exactly the right way to tell us something important. Part 12. The one explanation they can't measure. The AMS paper raises the possibility of what might be called an AI reporting amplification effect. It is, of all the explanations considered and dismissed in this analysis, the one that requires the most careful handling, not because it is the most plausible, but because it is the most modern, the most difficult to quantify, and the most easy to either overstate or dismiss without sufficient examination. So let us give it the examination it deserves, follow it as far as it can go, and then watch precisely where it stops. Here is the mechanism as the AMS describes it. In recent years, and particularly since the widespread adoption of AI-assisted discovery tools and social media amplification algorithms, witnesses to fireball events are being directed to reporting platforms faster and more efficiently than at any previous point in the database's history. The pathway used to look like this. Someone sees a fireball, they mention it to a neighbour, they maybe remember to Google it the next day, they find the AMS website after a few clicks, and they submit a report 24 hours after the event. Or they do not bother at all, because by morning the moment has passed and the impulse to document it has faded. The pathway now looks different. Someone sees a fireball and immediately opens their phone. They type a description into an AI assistant and are directed to the correct reporting portal within seconds. Someone else posts about the fireball on social media, and an algorithm identifies their post as relevant to hundreds of followers who also saw the event but had not yet thought to report it. Those followers submit reports. Someone in a community group mentions it, and a thread of responses follows, each one potentially generating another submission. The event that would previously have collected 40 reports over 24 hours now collects 140 in the first hour, not because more people saw it, but because the infrastructure connecting observers to the reporting platform has become dramatically more efficient. This is a coherent hypothesis. It is grounded in observable changes in how people interact with information and how algorithms surface content. It is not a far-fetched or dismissive explanation. The AMS takes it seriously enough to include it in their published analysis, which is itself a mark of intellectual honesty, because acknowledging a mechanism that might reduce the apparent strength of your own finding is not something institutions do when they are motivated primarily by self-promotion. And the hypothesis does explain some things. It explains why witness counts per event might be elevated beyond what the underlying physical events would produce on their own. It explains why the ratio of reports to events might be higher in 2026 than in 2016, even for events of identical physical magnitude. It provides a plausible mechanism for inflation in the statistical layer of the data, the layer that consists of human reports submitted through digital platforms, without requiring any change in the physical layer of the data, the layer that consists of actual objects entering the actual atmosphere. So far, so reasonable. Now let's follow it to its limit. The AI reporting amplification hypothesis, taken at maximum strength, assuming it is real, assuming it is significant, assuming it has inflated witness counts substantially across the anomalous period, can account for elevated numbers in exactly one category of evidence. Witness counts. That is it. That is the boundary of its explanatory reach. And the fireball anomaly of early 2026 is not built on witness counts alone. It is built on multiple independent lines of physical evidence that have nothing to do with how efficiently people are finding the MS submission form. Consider the sonic booms. 30 of the 38 large events documented in the analysis produce sonic booms, pressure waves generated by hypersonic objects penetrating deep into the lower atmosphere, physical disturbances in the air itself that shook windows, triggered car alarms, and sent people calling emergency services across multiple states. A sonic boom is not a report, it is not a submission, it is not a data point that exists because someone typed something into an AI assistant. It is a measurable physical event, recorded by seismometers, infrasound detectors, and the nervous systems of everyone within range of it. You cannot generate a pressure wave by optimizing your reporting workflow. The AI amplification hypothesis has nothing to say about sonic booms, because sonic booms are not produced by reporting behavior. They are produced by large, dense objects moving at hypersonic velocities through thick atmosphere. Consider the long-duration sightings, 1,693 events lasting 4 seconds or longer against a previous record of 651. Duration is a physical property of the fireball event itself, determined by the size and density of the incoming object and the angle of its atmospheric entry. A 4-second fireball lasts 4 seconds whether 10 people report it or 10,000. More efficient routing to the AMS platform does not extend the burn time of an incoming meteoroid. The duration data is not susceptible to amplification effects in the way that raw witness counts might be, because duration is measured per event, not aggregated across reports. Each long-duration sighting represents one event that lasted a physically significant amount of time. AI amplification cannot manufacture those events. Consider the meteorite recoveries. The Houston chondrite came through a roof. The Ohio eucrite was recovered from the fall site of the March 17th event. The Germany diogenite was recovered after the March 8th bolide. These are physical objects. They have mass. They have chemical compositions that can be analysed in a laboratory. They have mineralogical structures that record their formation histories and their time in space. No amount of social media amplification produces a eucrite. No AI assistant directs a rock through a ceiling. The recovered meteorites exist independently of every report ever submitted to every platform, and their existence as physical evidence of high-energy atmospheric entry is completely unaffected by how efficiently the digital reporting infrastructure is operating. Consider the HED anomaly specifically. 2 meteorites from the howardite eucrite diogenite family, representing approximately 3 to 4% of all meteorite falls, recovered within 9 days of each other from events on separate continents. The statistical rarity of this clustering is calculated from the base rate of HED falls in the global meteorite record, not from the number of reports submitted to the AMS. Whether 1 person or 1,000 people reported each event has no bearing on the chemical classification of the recovered rocks, or on the probability calculation that makes 2 HED falls in 9 days remarkable. Consider the Anthelian surge. Activity from this orbital source roughly doubled, reaching densities of approximately 9.6 events per 1,000 square degrees. This measurement comes from directional analysis of fireball trajectories, not from raw report counts. The orbital population that feeds the Anthelian source either produced more material intersecting Earth's path or it did not. The AI amplification hypothesis operates on the reporting layer of the data. The Anthelion surge is a finding about the physical distribution of incoming material in orbital space. These are different things. Consider the high inclination population. 11 events from above plus 70 degrees declination against a previous maximum of 5. Again, this is a directional finding derived from trajectory analysis. The orbital mechanics that determine whether an incoming object has a high inclination trajectory are not influenced by social media algorithms. Jupiter's gravitational perturbations do not care how efficiently witnesses are finding the AMS website. The AMS is explicit about all of this. They cannot quantify the AI amplification effect. They cannot assign it a precise numerical contribution to the elevated witness counts. They cannot rule it out as a partial contributor to the statistical layer of the anomaly. But they also note, with the careful precision of researchers who have thought this through, that even if you stripped away every single report that might have been amplified by AI routing or social media surfacing, even if you discarded the entire witness count dataset and started from zero, the physical evidence would remain, the sonic booms would remain, the duration records would remain, the meteorite recoveries would remain. The directional anomalies in the Anthelion source and the high inclination population would remain, and all of that remaining evidence would still require an explanation that has nothing to do with how efficiently people are finding the submission form. So the most generous possible interpretation of the AI amplification hypothesis is this. It may be making the anomaly look slightly larger than it actually is in the statistical layer. It may be inflating the witness count numbers by some amount that cannot currently be precisely determined. And if you are the kind of person who finds comfort in uncertainty, you could, at a stretch, argue that the true magnitude of the anomaly is somewhat smaller than the raw numbers suggest. But somewhat smaller than double is still a very large number, and you cannot amplify a sonic boom. You cannot socially surface a meteorite. You cannot algorithmically produce a eucrite. Something real changed in what is entering the atmosphere. The question of precisely how large that change is carries some uncertainty. The question of whether a change occurred does not. And once you accept that the physical change is real, once you follow the evidence past the point where reporting effects have any explanatory reach, the question of origin becomes the only question left. Something is sending this material. Something changed recently enough to produce the accelerating pattern we documented from January through March. And the data, when you follow it past every failed explanation to the hypothesis that actually survives, points somewhere specific. It is not a comfortable direction, but it is where the evidence leads. Part 13. The Unknown Debris Hypothesis. The AMS paper includes a phrase that I want to sit with for a moment before we take it apart. They describe the possibility of Earth intersecting an uncharacterized debris population. Read that carefully. Not a known stream, not a catalogued family, not an identified parent body. Uncharacterized. Meaning, it exists in the data, it is producing physical effects, and we do not know what it is. That word, uncharacterized, is doing a lot of work in a very small space. In scientific literature, word choices are deliberate. Researchers do not reach for dramatic language when precise language is available. And the choice of uncharacterized over any of the more comfortable alternatives tells you something important about where the AMS actually stands on this question. They did not write undetected, which would imply the debris field simply escaped notice due to observational gaps. They did not write unexpected, which would suggest surprise but not fundamental ignorance. They wrote uncharacterized, meaning the population may have been partially visible in the data all along, may have left traces in previous analyses but has not been systematically identified, measured, mapped, or understood. It is the scientific equivalent of saying, we know something is there because we can see what it is doing, but we cannot yet tell you what it is. That is a genuinely unusual position for a field as mature as meteor astronomy to find itself in. We have been systematically studying the near-Earth debris environment for decades. We have catalogued thousands of near-Earth objects. We have characterized dozens of meteor streams and identified their parent comets or asteroids. We have built global networks of sensors, cameras, and reporting platforms precisely to avoid being surprised by what is out there. And yet here is the leading scientific institution in civilian fireball monitoring, publishing a paper that describes the probable cause of the most anomalous fireball period in their recorded history as a population of debris they cannot characterize. The hypothesis works like this. somewhere along Earth's orbital path, or in the broader region of near-Earth space that Earth's orbit sweeps through over the course of a year, there is a concentration of debris that is denser than the surrounding environment and has not been systematically mapped. Earth, moving along its orbit at approximately 67,000 miles per hour, passed through or adjacent to this concentration in early 2026. As it moved through the denser region, it swept up more material than it typically encounters during that portion of its annual journey. The way a car driving through a swarm of insects collects more impacts per unit time than it does on a clear stretch of road. The material in this hypothetical concentration has specific properties that the data constrains. It is skewed toward larger fragment sizes. This is required to explain the distribution shift, the finding that the high-energy end of the fireball size spectrum increased disproportionately relative to the small event baseline. A concentration of uniformly small debris would elevate all threshold levels proportionally. The specific pattern of larger events increasing faster than smaller events points toward a concentration in which larger fragments are overrepresented relative to the background population. The concentration also spans multiple orbital populations. This is required to explain the simultaneous elevation of the Anthillian source and the high inclination arrivals, two dynamically distinct populations that should not be correlated with each other under normal circumstances. A debris concentration that is confined to a single orbital family would affect one directional population. A concentration that spans a range of inclinations and orbital geometries could simultaneously feed elevated activity from multiple directions, which is exactly what the directional data shows. And the concentration is not associated with any known meteor stream. This is required to explain the absence of a common radiant among the anomalous events. A stream has a radiant. An unstructured debris concentration does not. The events in the 2026 anomaly come from multiple directions without clustering around a single point in the sky, which is consistent with a diffuse, multi-directional debris environment rather than a coherent orbital stream. Here is what makes this hypothesis scientifically meaningful beyond its ability to fit the data. It is internally consistent across every line of evidence simultaneously. This is harder to achieve than it sounds. When you have 6 or 7 independent physical signals, threshold statistics, sonic boom frequency, duration records, meteorite recoveries, directional data from 2 separate orbital populations, a hypothesis that explains some of them while contradicting others is not useful. What you need is a framework that accommodates all of them without internal contradiction. The uncharacterized debris population hypothesis does that. Every piece of evidence we have discussed throughout this investigation is compatible with Earth having moved through a denser than normal, multi-inclination, large fragment-enriched concentration of untracked material in early 2026. Not merely consistent with 1 or 2 signals, compatible with all of them simultaneously. That is not a trivial achievement for a hypothesis built primarily on inference, rather than direct observation. But the limitation is real, and the AMS is careful not to overstate what compatibility actually proves. Fitting the data and explaining the data are different things. A hypothesis that is consistent with all available evidence is not the same as a hypothesis that has been confirmed by independent observation. The uncharacterized debris population has not been directly detected. We have not pointed a telescope at a region of space and measured an elevated density of material. We have not tracked individual members of the hypothetical concentration and confirmed their orbital parameters. We have not predicted where the concentration ends and verified that fireball activity returned to normal when Earth moved past that boundary. The hypothesis is inferred from its effects not observed directly. And inference, however well supported, carries a different epistemic weight than direct detection. This is not a flaw unique to this particular hypothesis. Much of what we know about the near-Earth debris environment is inferred from effects rather than directly measured. The vast majority of meteoroids that enter Earth's atmosphere are too small to be detected in space before arrival. Even objects large enough to produce significant fireballs routinely escape detection until they are already burning. Our planetary defense surveys, as sophisticated as they have become, are optimized for objects large enough to pose regional or global threats, the ones that could devastate a city or worse. The population of meter-scale and sub-meter-scale objects, the ones responsible for the kind of fireball activity we have been discussing, remains dramatically undercharacterized. Not because we are not looking, but because there are so many of them, they are so small relative to the distances involved, and they move so fast that systematic characterization of the population at this size range is genuinely difficult. Which means that an uncharacterized debris concentration at this scale is not implausible from a detection standpoint. It would not necessarily have shown up prominently in existing survey data. It would not necessarily have been flagged by planetary defense monitors focused on larger threats. It could have been circulating in near-Earth space, gradually converging with Earth's orbital path, without triggering any of the detection systems designed to catch things that are trying to hit us at civilization-threatening scales. There is something quietly unsettling about that. Not because the debris population represents a catastrophic threat. The events of early 2026, dramatic as they were, caused no mass casualties and no major structural damage beyond one roof in Houston, but because it represents a gap in our understanding of the environment immediately surrounding Earth. We like to think we have a reasonably complete picture of what is out there in near-Earth space. We have catalogued thousands of asteroids. We have characterized the major meteor streams. We have built networks to detect and track incoming objects. And yet, if the AMS hypothesis is correct, a debris concentration large enough and dense enough to produce the most anomalous fireball period in 20 years of recorded history was circulating in that environment without systematic characterization until Earth drove through it, and the fireballs told us it was there. The sky notified us. The database caught it. And the researchers published it honestly. What the hypothesis does accomplish, beyond fitting the data, is reframing the question in a way that points toward the next level of investigation. If the debris concentration exists, it came from somewhere. Debris does not spontaneously appear in near-Earth space. It does not condense from the vacuum or materialize from nothing. It is the remnant of something that was once larger, a body that was disrupted, a collision that sent fragments onto new trajectories, an event that occurred at some point in the recent or distant past, and whose consequences are now arriving at Earth's doorstep in the form of sonic booms and recovered meteorites and fireball counts that double at exactly the thresholds where they should not. Something broke. Something sent its pieces into orbits that converge with Earth's path. And the question of what broke and when and where is not merely academic, because the answer determines whether the debris concentration Earth moved through in early 2026 is a one-time encounter or the leading edge of a longer-term change in the near-Earth environment. That question has a specific and testable answer, and it involves two unusual rocks, one very large asteroid and a laboratory test that may already have produced results that nobody has published yet. Part 14. The Parent Body Scenario. 4. Vesta is not a household name, but it is one of the most significant objects in the asteroid belt. It is the second most massive body in the belt, roughly 525 kilometers in diameter, and it is ancient, a relic of the solar system's first few million years, preserved in a way that allows us to study planetary formation processes that would otherwise be completely inaccessible to us. Its surface has been heavily mapped. Its composition has been characterized spectroscopically, and we know from those spectroscopic measurements and from decades of meteorite analysis that a significant fraction of the rocks that fall to Earth originated from Vesta or from the family of smaller asteroids called Vestoids that were knocked off Vesta by ancient impacts and have been drifting through the solar system ever since. But before we get to the meteorites and what they might be telling us, let me give you a proper introduction to Vesta itself, because this object deserves more than a passing mention. Most asteroids are, in geological terms, relatively simple. They're undifferentiated, meaning they formed as roughly uniform mixtures of rock and metal that never got hot enough internally to undergo the kind of large-scale melting and separation that transforms a primitive rocky body into something more complex. They are essentially the same material all the way through, preserved in roughly the state they were in when the solar system was young. Vesta is not that. Vesta is something considerably more interesting. In the first few million years of the solar system's existence, when the rocky bodies of the inner system were still accreting and growing, the most energetic process shaping them was the decay of short-lived radioactive isotopes, particularly aluminum-26, a radioactive form of aluminum that was abundant in the early solar system and released enormous quantities of heat as it decayed. Bodies that formed quickly enough, while aluminum-26 was still present in significant quantities, received an internal heat source powerful enough to melt them from the inside. And when a rocky body melts internally, something remarkable happens. It differentiates. The heavy materials, primarily iron and nickel, sink toward the center under gravity. The lighter silicate minerals float toward the surface. The body develops layers, a metallic core, a rocky mantle, a crustal surface, in a process that mirrors what happened inside Earth and the other terrestrial planets, just at a much smaller scale. Vesta underwent this process. It developed a metallic core. It developed a mantle of dense magnesium-rich rock. It developed a basaltic crust of solidified lava flows. It became, in miniature, a differentiated planetary body, a protoplanet that was well on its way to becoming something like Mercury or Mars before the formation of Jupiter disrupted the asteroid belt and prevented any further planetary growth in that region. Jupiter's gravitational influence stirred the belt too violently for the remaining material to accumulate into a planet. Vesta was left stranded, a world that started the process of becoming a planet and then froze in place, geologically speaking, while the actual planets continued evolving around it. This is why Vesta is so scientifically valuable. It is a window into the interior processes of early planetary formation, preserved in a state that Earth's own geological activity has long since erased. When researchers study Vesta's surface composition from spacecraft data, or when they analyze the meteorites that originated from Vesta in Earth-based laboratories, they are effectively looking at the interior of a primordial planet, examining rock types that formed at different depths within a differentiated body during the solar system's first few million years. The HED meteorites, howardites, eucrites, and diogenites are the primary record of this window. Eucrites are basaltic rocks that formed at or near Vesta's surface, the product of ancient lava flows that solidified on the crust. Diogenites are coarser-grained rocks that formed deeper, in the lower crust or upper mantle, where cooling was slower and crystals grew larger. Howardites are impact-generated mixtures of the two, produced when meteorite impacts on Vesta's surface churned eucrit and diogenite material together. Each type tells you something about a different depth within the same parent body, and the spectroscopic match between these meteorites and Vesta's surface composition is one of the most robust source identifications in all of meteoritics. Now let us bring the Ohio eucrit and the Germany diogenite back into focus, because understanding what Vesta is makes the coincidence of two HED falls in 9 days considerably more loaded than it initially appears. The eucrite from Ohio, recovered following the March 17th event, is a piece of Vesta's crust. The diogenite from Germany, recovered following the March 8th bolide, is a piece of Vesta's mantle or lower crust. Two rocks from different geological layers of the same parent body, falling on different continents, within 9 days of each other, in the same month that the American Meteor Society confirmed the most anomalous fireball period in 20 years of recorded data. The 3 to 4% base rate of HED falls in the global meteorite record makes each individual fall notable. 2 falls in 9 days elevates the coincidence into the territory of a signal that demands examination. The apparent contradiction in their arrival directions, radiance separated by approximately 98 degrees, nearly a right angle in the sky, initially seems to argue against a common recent origin. If both rocks came from the same place, why are they coming in from such different directions? This is the question that makes the naive version of the common origin hypothesis difficult to defend, and it is worth taking seriously rather than dismissing. The resolution lies in understanding how debris from a disrupted body actually behaves over time, and the timescales involved are long enough that human intuition tends to underestimate them dramatically. When a large object in the asteroid belt is disrupted by an impact, whether partially losing surface material or catastrophically fragmenting entirely, the resulting debris does not travel in a neat collimated stream forever. In the immediate aftermath of the disruption, the fragments do cluster in orbital space. They share similar orbital parameters because they all started from the same place, with velocities that were perturbations on the original body's orbit rather than completely independent trajectories. Early in the dispersal process, the debris would produce a relatively tight stream, arriving at Earth from a narrow range of directions. But the solar system is not static, and orbits are not permanent. Every fragment in the debris cloud is subject to the same gravitational forces that shaped the original body's orbit, plus additional perturbations specific to its new, slightly different trajectory. Jupiter's gravitational influence, operating through mechanisms like mean motion resonances and secular resonances, gradually modifies orbital parameters, eccentricity, inclination, the orientation of the orbit in space, at rates that vary depending on the specific orbital characteristics of each fragment. Over thousands of years, the debris cloud begins to spread. Over millions of years, it can disperse into a broad, diffuse population that spans a wide range of orbital geometries while retaining a common chemical signature. This is how asteroid families work. The Vesta family, the Vestoids, the smaller asteroids that share Vesta's spectroscopic characteristics, spans a recognizable but not perfectly clustered region of orbital parameter space. They share a common origin in the sense that they were all knocked off Vesta by impacts, but they do not all share identical orbits, because millions of years of gravitational evolution have spread them. Two Vestoid fragments that arrived at Earth from 98 degrees apart in declination would not be surprising if their separation from the parent body happened long enough ago. The critical question is timing, and this is where the cosmic ray exposure age analysis becomes the potentially decisive test. When a rock is embedded within a larger body, it is shielded from the high-energy cosmic rays that constantly stream through interplanetary space. The bulk of the parent body absorbs the radiation before it can penetrate to the interior. The moment a fragment breaks free and begins traveling independently through space, that shielding is gone. Cosmic rays begin interacting with the rock's mineral structure, producing specific isotopes through nuclear reactions that would not occur inside a shielded body. The longer the fragment travels independently, the more of these cosmogenic isotopes accumulate. By measuring the ratio of cosmogenic isotopes to stable reference isotopes in a recovered meteorite, researchers can calculate approximately how long that specific rock has been an independent object in space, its cosmic ray exposure age. If the Ohio Eucrit and the Germany Diogenite have similar cosmic ray exposure ages, if the isotope ratios in both rocks point to roughly the same duration of independent space travel, that convergence would be powerful evidence for a common originating event. It would mean both rocks were liberated from their parent body at approximately the same time by the same disruption and have been travelling on their independent trajectories ever since. And if that exposure age is relatively short, thousands to hundreds of thousands of years rather than the billions of years that would suggest ancient Vesta family membership, it would point toward a recent disruption event, one that occurred in the geologically recent past and injected fresh Vesta family material onto Earth-crossing orbits. The researchers who can answer this question are working right now. The recovered meteorites are in laboratories. The isotope measurements are either complete or underway. The cosmic ray exposure ages may already exist as numbers in a spreadsheet, being checked and cross-referenced before anyone commits them to a publication. If those numbers match, if both rocks point to the same event, the same moment of disruption, the same starting gun, then the implication is as clear as it is significant. Something in the Vesta family broke recently. Not billions of years ago in the solar system's violent youth. Recently. And the pieces of whatever broke are arriving here now, announcing themselves through rooftops and sonic booms and the careful analysis of scientists who had the data to recognize them for what they are. Something broke. The chemistry of the rock says so. The timing of the falls says so. And if the laboratory results confirm what the hypothesis predicts, then what we are watching in early 2026 is not a random fluctuation in the ancient debris environment. It is the arrival of fresh material from a specific recent event, material that was, until recently, part of something larger, something that no longer exists in quite the same form it did before. The question of exactly when it broke and what broke it is the one the exposure ages may finally answer. Part 15. The timing problem. January of 2026 showed a mild increase in fireball activity above the historical baseline. Noticeable, but within the range of year-to-year variation. February was more pronounced, clearly elevated, clearly above what seasonal effects alone could explain, but not yet dramatically so. March was extraordinary. The numbers we have been discussing throughout this script, the doublings, the record-breaking witness counts, the HED falls, the sonic boom frequency, that is March. The escalation is not linear, it accelerates. And that acceleration pattern is itself a data point. A gradual increase from January to March is not what you would expect from a sudden discrete event, an asteroid collision say, that instantly flooded a particular orbit with fresh debris. A sudden discrete event should produce a relatively sudden onset, not a 3-month ramp. On the other hand, a perfectly linear and gradual increase might be more consistent with Earth's orbit slowly converging on a stationary debris field. But the acceleration pattern, mild, moderate, extreme, suggests something more dynamic. It suggests either that the debris field Earth is encountering has internal structure, with a denser core that Earth has not yet fully entered, or that the source of new material is itself ongoing rather than being a single past event. There are speculative frameworks for what could produce this kind of temporal pattern, and I want to flag them clearly as speculative. Some researchers have pointed to orbital resonance dynamics in the asteroid belt, where the gravitational influence of Jupiter periodically stirs material into Earth-crossing orbits in structured waves rather than as a continuous flow. Others have noted that some classes of asteroid disruption involve not a single fragmentation event but a cascade, an initial impact that weakens a body, followed by secondary rotational breakup as the object's spin rate increases under thermal pressure from sunlight, a process called the Yorp effect. A cascade disruption would produce material on a timescale of years to decades, not instantaneously, and could produce the kind of accelerating influx pattern we seem to be seeing. There is also the interstellar object hypothesis. I will give this exactly the amount of space it deserves given the current evidence. It is possible, it is not supported by the specific data from this period, and I mention it only because it appears in the background of every conversation about anomalous fireball activity and deserves an honest assessment rather than either breathless promotion or dismissive silence. An interstellar interloper passing through the inner solar system could gravitationally scatter material from the asteroid belt onto Earth-crossing orbits. The timing could, in principle, fit. There is no direct evidence for this. I am moving on. What the timing data does suggest fairly clearly is that whatever caused the anomaly was not happening billions of years ago and is not purely the product of ancient solar system dynamics. The escalation from January to March implies a change that happened recently enough to produce a detectable ramp. Something changed in the recent past, perhaps the very recent past, and what we are seeing now is the material result of that change arriving at Earth's doorstep in real time. The trajectory of the anomaly through the first quarter of 2026 points toward a discrete originating event, a source that was set in motion not in deep geological time, but within a time frame that might actually be constrainable. That is both scientifically exciting and, if you think about it carefully, worth paying close attention to. Something changed recently, and the sky above us in March of 2026 was the proof of that change, written in light and sound and rock. Part 16. The sky is getting busier. On a date that falls within the same extraordinary window we have been examining, a Starlink satellite designated 34,343 fragmented at an altitude of approximately 560 kilometers. Leo Labs, the commercial space tracking firm that monitors low Earth orbit, detected tens of debris fragments spreading from the fragmentation event. This was not an isolated incident. It was the second comparable satellite fragmentation event in a period of approximately 3 months. Now, I want to be precise about what this means for the story we have been telling, because it would be easy to conflate two very different phenomena that happen to be occurring in the same time window. Artificial satellite debris fragmenting in low Earth orbit is not the same as natural meteoroids entering the atmosphere from interplanetary space. The Starlink fragmentation is happening at 560 kilometers altitude, in orbit, where the debris will circulate for weeks to years before atmospheric drag degrades its orbit enough to cause re-entry. When those fragments do re-entry, they will burn up as artificial fireballs, bright luminous streaks that look to an observer on the ground very much like natural meteors. And in a period when fireball reporting platforms are already experiencing elevated submission rates, artificial re-entries add noise to a signal that is already difficult to interpret. The connection back to the central question, has the size distribution of natural meteoroid material changed, is this. Satellite debris is a confounding factor. It cannot explain the sonic booms from the Ohio asteroid. It cannot account for the diogenite recovery in Germany. It cannot produce HED meteorites. The physical and chemical evidence we have examined throughout this script is not subject to confusion with artificial re-entries. But from a public observation standpoint, a fireball is a fireball until someone analyses it. and the increasing density of artificial objects in low Earth orbit means that the overall fireball environment, the one that generates headlines and public attention, is becoming harder to pass. There is also the longer-term concern that increasing satellite density raises the baseline probability of collision cascades in low Earth orbit, a scenario where one fragmentation event generates debris that causes additional fragmentations in a chain reaction. The Starlink event and its predecessor 3 months earlier are reminders that this risk is not theoretical. It is happening, at a modest scale, right now. None of this is the cause of the natural fireball anomaly. I want to be completely clear about that. The uncharacterized debris population, the potential Vesta family disruption, the Anthelian surge, the high inclination population. These are phenomena of interplanetary space, unrelated to anything happening in low Earth orbit, but they are occurring simultaneously. The sky above Earth in early 2026 is dealing with elevated natural infall from space, elevated artificial debris in orbit, and an analytical community trying to separate signal from noise across both populations at once. The observation environment is becoming more complex. The anomaly is confirmed and real, and the two things are not the same problem, but they are both happening right now in the same sky. Here is what we know. The American Meteor Society published a dataset analysis confirming that the fireball anomaly of early 2026 is statistically real. The signal intensifies at higher detection thresholds, which eliminates reporting bias as a primary explanation. 79% of large events produce sonic booms, confirming that physically larger objects are penetrating deeper into the atmosphere. Long-duration sightings reached 2,693, more than 2.5 times the previous record, providing a second independent physical confirmation of elevated object size. 2 HED meteorites fell within 9 days, representing a statistically unusual concentration of a rare meteorite type that accounts for only 3 to 4% of all falls. The Anthelian source doubled its activity, high inclination arrivals more than doubled, and every alternative explanation, increased reporting, new showers, seasonal effects, observational bias, was tested against the dataset and found insufficient. Every independent line of evidence points the same direction, not because they were selected to point that way, but because they are each measuring something real from a different angle, and they all converge. Here is what we do not know. We do not know the source. We do not know whether the leading hypothesis, Earth intersecting an uncharacterized debris population, identifies the right mechanism or only gestures toward it. We do not know whether the Vesta family HED falls represent a recent fragmentation event or a coincidental clustering of ancient material. We do not know what set the escalation in motion between January and March. We do not know how long the anomaly will continue, whether the March 28th Washington State fireball represents a continued trend or a tapering off, whether the debris density Earth is encountering will remain elevated or has already begun to diminish. The AMS does not know either, and the thing I keep returning to, the thing that makes this paper different from most scientific publications I read, is that the AMS says so explicitly. They present their findings, they test their explanations, they describe the leading hypotheses, and then they acknowledge, in the measured language of careful scientists, that the data has brought them to a frontier they were not expecting to reach. We live at an extraordinary moment in human history from the standpoint of planetary observation. There are more fireball cameras, more reporting networks, more space-based sensor platforms, more sky survey programs scanning for near-Earth objects than at any previous time in recorded history. We can detect things now that our grandparents would never have known had happened. We are watching the solar system in higher resolution than any prior generation of humans, and yet here is the AMS, operating the largest civilian fireball database on Earth, with continuous data spanning more than 20 years, having applied every methodological tool available to them, and arriving at a conclusion that is, in its honest and complete form, the following. Something changed in what is falling toward Earth, and we do not yet know what caused it, where it is coming from, or when it will stop. The sky above Earth right now is not the same sky it was a year ago, not statistically, not physically, not chemically. Something shifted in the distribution of incoming material, in the orbital populations contributing to it, in the energy being deposited into our atmosphere by objects arriving from interplanetary space. That shift is confirmed. It is real. It is ongoing. The most monitored sky in human history has just told us something unexpected, and we are only beginning to understand it.